notice they will see.
Okay, I remind you where we were yesterday. We wanted to describe the standard model of particle interaction as a almost commutative geometry.
Can I ask some light?
Yeah, is that light from the board work, right?
Board or whatever.
Well,
Very dark.
yes, but you have to look at this.
Background very.
Okay. Can you see still anyways? Okay, so I wanted to describe the standard model. This is the zoo of elementary particles. So it's a gauge theory based on this group, which I write also as this. And I remind you what I told, which I didn't show you, that this zoo of elementary particles with particular representations of the group can be reproduced, can be put into an Hilbert space, and this Hilbert space can support representation of the algebra with all the right, which follows all the right rules. This is not automatic. The representation is, however, at some point, from a mathematical point of view, trivial, in the simple, because it's a 96 by 96 matrix with blocks. And there is the doubling, and I wanted to see if there was some other, see all the constraints that this one I say, and the Dirac operator will contain the masses of all the particles. So I take this as a, okay, I take as a fermionic action the one with this covariant Dirac operator, and again I can manage to satisfy all of the axioms or the properties in a fortuitous way. So this is the action, and you find all of the mass terms for the fermionic action. Now let me discuss in more detail the bosonic action, because the bosonic action is more, it has more ramifications. So as I said already, this is, the 1/2 is missing, I forgot to put it. Actually the file was here and I didn't have access to it. So there is a 1/2 here. So it's basically, if I take this chi to be this function, the step function on the interval, so this is the number of eigenvalues smaller than this quantity lambda. Now lambda is a dimensional quantity, so it has the dimension of an energy, and it's a cutoff. Without, because I cannot take traces of unbounded operators, and so I regularize it in this way. So I want, however, to describe this in terms of the potential. Okay, the potential, as I said, will contain the bosonic particles of the theory. So I have the fermions, which are the matter content: electron, muon, quarks, electron, neutrino, quarks, repeated in 3 generations. But then I have another set of particles. They are not the matter, although some of them may have mass, which are the ones which exchange the interaction. So 2 electrons, now for the mathematicians, I'm being probably elementary for a physicist. 2 electrons will interact because there is a field between them, and quantum mechanically this field means that they are exchanging a particle, which is called the photon. Now this is a U1 gauge theory, and it's the simplest one. And there are 3 interactions. The other 2 interactions are non-abelian. So the photons, which are the elements of the connection, are promoted to be, in the case of strong interaction, the gluons, and this is SU3, the particles belong to the adjoint representation, and there are 8 gluons. In SU2, instead, there are 3 of these particles, and they are called the W. Now there is another complication. SU2 is a broken group by the Higgs, which we are going to discuss here. So what happens for a mechanism that I have no time to describe, but in the Lagrangian, the W particle gets a mass. So when it was discovered, it was said that they are like heavy light, because they are like light because they are interchanged, but they are heavy because they have a mass. Those particles have mass quite high, and they were discovered at CERN by a predecessor of LHC called LEP in 1979, something like that. So it took then, from 79 to 2015, it took 35 years to finally put the last particle, which was the Higgs.
Sir,
Yes.
in standard model, is there any connection between the parity violation and symmetry breaking sector of?
Yes. The parity,
No, I mean, old formulation of standard model,
Yeah.
there is any connection, the parity violation and symmetry breaking sector in electronic?
the theory, and this is an important thing, is chiral.
Yeah.
So it's,
But their chirality are automatically occur from the Higgs sector, no?
that is, the theory is chiral.
Yeah.
So chiral means that the left sector is not the same as the right sector. So this is a breaking of parity. So the particles which move like that, it's an imprecise way of saying, are different from the particles that move like that. But for particles move like that, there is an antiparticle that moves like that. But so the left-handed neutrinos are different from the right-handed neutrinos, and this you could see because in my description of particles, I was treating the left with the right-handed.
No.
So this is the breaking of the
For
particle.
neutrino case, neutrino in standard model, neutrino are massless.
Yes.
So only.
I'm
left-handed-
here standard model with right-handed neutrinos. I put
So
right-handed
neutrino
neutrinos.
is massive.
Is massive, but
Oh.
still they are different. The left-handed are much lighter than the right-handed.
So chirality is not called the.
There is the theory breaks parity.
Yeah.
This was discovered by Li and Yang in 1960 or something like that. So the theory breaks parity. The universe is not parity invariant, and so if we communicate with some distant aliens, we can decide which is left and which is right by just saying that we can see only light left-handed neutrinos, and so if we don't agree on parity, it means that they are made of antimatter. Okay, because antimatter has everything reversed. So if we don't agree on if their matter is the other way around, it means that they are made of antimatter. But the photons don't care if the.
No, in standard model, old standard model, not Cohn's formulation of standard model, the Higgs sector are put by hand. But here
Yes.
Higgs sector
Is
are
not put
not
by
geometrically
hand.
is coming. So
Yes.
chirality of the electric sector
Yes.
is originated from the occurrence of the Higgs sector.
No, because I already put the particle in a chiral way. See, this is my starting point. So I already have put that the right-handed particles behave differently from the left-handed particles. So I take a starting point, the knowledge of the matter sector. So I take all of the fermions as my starting point. So this theory is chiral. And this is actually one of the reasons for which the representation is very complicated. Because I have to respect the fact that the right-handed quark has an hypercharge of 4/3 and the left-handed has an hypercharge of 1/3. So I have to satisfy all those things. So the standard model is a miracle. There is something which I didn't mention, which is the fact that these theories would have anomalies, which are violations of symmetry. They would be very bad if a quantum mechanical theory has an anomaly. But miraculously, the standard model has all of these numbers so that the anomalies in different sectors, so different symmetries, the anomalies in this symmetry, they perfectly cancel each other. So if any of these numbers had been different, if this had been 1/3 instead of minus 2/3 or something, the theory wouldn't be coherent, wouldn't be consistent. And so this is, however, this theory with all these idiosyncrasies of all these representations of the groups intersecting, etc., those carry a representation of the algebra of 3x3 matrices, quaternions, and complex numbers. That commutes with the representation on the other side. So in this way, I don't want to put the particle because it takes you some hours to be sitting and marveling at it, but at some time you start seeing the beauty of it. So I want to make clear, some of the things are assumptions, and then we will see what we can get out of it, okay? And the assumption is that I have a Hilbert space which carries a certain representation of an algebra. And this is the assumption. The Hilbert space is the Hilbert space of fermions. And the algebra will give me the bosons. Gives me the bosons with this fluctuating, this fluctuating operator, because this A is something which I calculate cranking a machine. A is a one form, and one forms are generic elements of the form of this form. A one form is something which I calculate by doing as I say, one forms are elements of the kind sum over A, AI, D, BI, where those are elements of the algebra. So I know how those things are. All I need is the algebra and the Dirac operator. So this gives me what are all of the bosonic elements. And I do find that there is one photon, two W's and one Z. Okay, one particle like the photon, three W's. There is some mixing between them, and 8 gluons, and the Higgs. And it comes just by doing this. And the Higgs is the off-diagonal elements, as I shown in the 2x2 case. It's really is the same because it's the one between the left and the right sectors.
So according to Cohn's lot model, all gauge boson are associated with the Higgs boson.
Yeah.
So all are unified.
Yes.
So but Higgs boson associated with coming as a gamma 5 times phi. Gamma 5 tensor product phi. So in connection,
Yes.
gauge boson coming as a plus gamma 5 tensor phi.
Not in the connection, the Dirac operator.
And Dirac operator, right?
Yes.
So gauge boson, it comes associated with the chirality operator. So since the electric sector are chirality violating or symmetry violating, so the chirality of the mass, each particle, the
Yeah.
left chiral or right chiral are different when particle have massive.
Yes.
So particular the mass of the particle are originated from the Higgs sector, no?
Yes.
That is why the chirality are breaking.
I don't understand what is what the masses appear in the standard model, in the Dirac equation. Masses are objects which take a left-handed antiparticle, then you put a mass which actually will be the Higgs field times a Yukawa coupling. So this is what gives a mass times ER. So you need a chiral theory and you get the mass here.
Okay.
And you get everything. So you get the standard model. So I mean, now, you get the Nobel Prize by predicting one particle, the mass of one particle, because you go one step forward. I don't think anybody can get the Nobel Prize by getting everything together in one go. So we start from something, which is we know something, and then we do a step forward. You know? So it's like, you know, in one go. It's not that it's too ideal that from one first principle you find the standard model. This is, I don't know, number theory. You just not even that, because Russell Whitehead just to go from one equal to take a few hundred pages, and so we start with some observations of nature, and then we explain something. So we start with the fermions that we know, and with the algebra, and we try to go ahead. And but now, okay, now you'll have fun, because now we go into the bosonic action, and we go into this infinite dimensional world, and field theory and renormalization. And I'll try to be self-contained. So, this is my bosonic action. It's a regularized trace based on this, and this is a function of this potential. So, although what it is the number of eigenvalues, so 1/2 of the number of the eigenvalues up to a certain level. Of course, if I change the potential, the 1/4, then this number will change. So it's a number, so it's a function of this connection. And I want to express things in terms of the potential 1/4, the curvature, the spin connection, the Riemann tensors, etc. So I want to express things in terms of these fields which get together, and they are the particles. And what particles are there, as I say? The photon, 3Ws, it's not completely precise, the B particle, 3Ws, and the gluons. And then I have the curvature of space-time, which for me is a background. I will not quantize it. But so everything will depend on this. So there is a technique which is called the heat kernel, which I will briefly describe, and basically is based on doing a Taylor expansion of this SB. Now this SB is a function of the Laplacian, which in turn is a function of this A. So one writes this as a Taylor expansion in terms of these powers of this lambda square, and the Fn are the momenta of this chi, this function chi. So there is an F0 which is dxx times chi, F2 chi, and then the other one are the derivatives at the origin. That's why I say that actually this function is not very good, because I would technically need a asymptotic analytic function. But I will assume that if this is well approximated by an analytic function, you will see that basically this number, the first few numbers will not change. Now,
So what is the contribution from the fluctuation?
they are in the Laplacian.
So this is dA, right?
dA square.
dA squared, yes, yes, yes. It's dA squared. I'm sorry. There are two standard notation. One is to call D and dA, and the other is called D0 and D. So since I take it from different papers that I have written, sometimes I copy from one paper in which I used one notation, and from sometimes I use the other one. So this is dA.
Okay, so these ANs are functions of okay, so they depend on this.
Yeah,
this one, right?
I'm sorry. It's an expansion in lambda, so there is a lambda here. Okay, so yeah, this is I put because in general, people that do field theory, the heat kernel is a fairly standard thing. So this equation should be SB equal Fn, which has to do with chi. Okay. Then An, which has to do with the Laplacian, and then a lambda to the power n. So it's a Taylor expansion in this parameter. And based on this, now these coefficients are called the Seeley-DeWitt coefficients. If the manifold has no boundary, they vanish for n odd, and they have been calculated by Seeley and DeWitt with techniques, and the heat kernel technique predates anything by Kohn or other things. It's just ways in which one treats Laplacians. So the Laplacian knows a lot about the geometry, and the Laplacians in a Faber bundle knows a lot about the bundle, and knows especially about the curvature of the object. So if it's a bundle, there will be the curvature even to the base and the curvature even to the connection on the fiber. And so one studies this kind of thing. So there is a term which is a Laplacian, then there is another term which is a derivative, and there is another term which has no derivative. And these things have been calculated by Seeley and DeWitt, and it's just, I don't know. It's a complicated thing. It's,
Alpha and beta depend upon the gauge field.
if you have a Laplacian of this kind, you can do a heat kernel expansion. Okay? For any function, this is a function of the spectral action is a function, is a particular function of the Laplacian. Okay? Chi. So if you have a function of a Laplacian, which depends on a scale, you can make a Taylor expansion of this kind. And you can calculate these coefficients.
Why didn't you write covariant derivatives?
Because the heat kernel expansion is done in this way. It's the same. I can express if I have a covariant derivative, I can always express this in terms of this.
But there are extra terms.
Extra term.
No, they are in beta, alpha and beta. I'm not telling you what alpha. I'll tell you in the next. Thing. But if you write dA squared expanding, okay. So dA is there is an I, then there is d mu, then there is something which is a mu, a gauge connection. So d mu, gamma mu, a mu, gamma mu, plus, and then there is the spin connection, okay, and that's all. This of course has lots of indices there. This is a big matrix. Then you take the square of this, and there will be one term which is d mu d nu, coming from the square of this term, no? And this will give this, and then there will be, you are taking the square of this, there will be some terms with one derivative, some terms with zero derivatives, And the terms with zero derivatives will be connections of these omegas and everything. But, so, the Laplacian will be of this form. Okay? If the Laplacian is of this form, then I can use the techniques of the Hit kernel. And I can calculate this Seeley-DeWitt. Now, the calculation of the Seeley-DeWitt is a long and complicated thing. We invited Vasilievich to give a series of lectures around the third lecture. It takes 3 lectures to tell how to calculate why things are these ones. And for me, see, there are this beta. I can define omega, which is this with the Christoffel symbols. I can define omega mu nu, which depends again on the... And then here in beta, there are all of the terms which come from this connection. Okay? So you do the calculation, it's just a straightforward calculation. And you calculate this Seeley-DeWitt coefficients. And you see that the first one is a constant. So it's like a cosmological constant, although this number is very large. But then in renormalization you subtract things. I will say something later on. Then there is a first term which contains R. This is the Riemann-Hilbert action basically. And contains E. That E contains this beta, which contains all the terms of the kind A mu, and as I will see later on. And then I have another term in the expansion, and this other term contains all, this is the covariant derivative. So covariant derivatives of course appear, and you will see that there are terms which contain square and derivative of the richest scalar, and terms which contain the square of this, and they will give f mu nu. This is a general slide of the Hit kernel technique. So you do, it's a cranking a machine, but you see that if you have this kind of function, then this is different from 0 and is basically 1/2. This is 1. The first of this is 1. But then if you start horizontal or nearly horizontal, if it's analytic, it cannot be exactly horizontal, all the terms from F4 on will be negligible. Okay, so the form of this chi tells you that there are only the first 3 terms. So the expansion is not infinite, or rather it is, but the other terms are as suppressed as I want. So this simplifies the calculations.
F is compactly supported.
What is F?
Chi.
Chi? No, because it's cannot be because it's analytic.
You want to vanish fast at infinity, no?
Okay. The proof of this is done for an analytic function. Okay? But in order to make my life easier for calculation, I would like this function. So I take a function which is as close as the step function as I want. And so I can, these 3 numbers can be 1/2, 1, these 3 numbers can be 1/2, 1, 1 and 1, can be as close as 1/2 as 1 and 1 as I want. So I take them to be 1/2, 1 and 1, just for...
Do you need to put explicit form of some analytic functions?
No, because I'm making an expansion.
So
it's an expansion. Yes, but in order to prove this Seeley-DeWitt and actually Lishnerovitz, in order to prove that this expansion gives this blah blah blah, this is done for analytic functions. And therefore, I mean, no, but if the function is analytic, this series will be infinite. but I don't want this, because then there will be terms R to the 4 and so on, and I wouldn't know how to deal with them. But I can say that they are as small as I want, so I will ignore them.
The larger eigenvalue of the Dirac operator is not contributing.
Huh?
Larger eigenvalue of the Dirac operator.
No, I have a cutoff.
Cutoff.
So everything goes up to a point, and nothing against lambda. Okay, now this was the end of the second lecture, and the references are, okay, the standard model is in several books, for example, Schroeder. Then this book is actually covers what I'm saying from Walter van Zulekom, and the original spectral action appeared in Chamseddine and Kohn. Fermionic tumbling was our contribution in Naples. The part which I skipped was my contribution with Andrianov. The standard model before the Higgs discovery is in this paper, and the standard reference for the heat kernel in this context is Vassilievich, the manual. And then there is a connection with the zeta function, which is in my paper with Kurkov, Sakellariado, and Wachstrand it's already 3 years ago. Okay, so now I will, now starts the third lecture. I'm actually not doing so bad. Start the third lecture, which is confronting with reality. Okay, and as the reality as the nasty characteristic of being complicated and showing no respect for mathematics, in the sense that things would be mathematically pristine, and I don't. And of course, but mathematics doesn't show any respect for physics, because things in physics are messing up the mathematics. And anyway, so from this tension we can go on. Now, action and renormalization. Now, I'll tell you one of the reasons for which the standard model à la Kohn is not as popular among physicists as it should. And the reason is the following, because Alain Kohn is a mathematician. And when you write the action of the standard model, you write it with certain numbers. So the action of the standard model, after all, after I will have the thing, has various terms. And the various terms are, I schematically show some of them. There are terms of this kind, psi bar, or electron, say, electron bar. Then there is something which is the mass of the electron times ER. Okay? And this is there is one for the electron, one for the muon. Each particle will have this kind. Then there are terms of this kind, minus 1/4 F mu nu, which is F mu nu in turn is d mu. There is a coupling constant here, alpha, d mu a nu minus d nu a mu minus, actually alpha is here, 1 or minus alpha, commutator between a mu and a nu. Now concentrate on these objects. You look at it and they are numbers. So one could imagine that if I know, and this is true, if I know these numbers, then I know the theory and I can make predictions. Because then after, when you write this action, you give it to phenomenologists that have an industry of this, and they calculate the probability that if I smash one particle against another particle, something else will come out. And there will be terms of this kind also, which couple different EL, A, ER, and they will, there are gammas here, and they means that I am coupling the electron to the photon for the W, okay? Not to the gluon, because it's not there. So you would think that I write this action and everything is fine. Now, we know how to do with this field theory in a perturbative way by making an expansion in the expansion of the path integral of the action in various terms, which can be diagrammatically described by lines and vertices, and this is the great contribution of Feynman. So the Feynman diagrams, which are not really what everybody thinks is a picture of what is happening. They are a graphical way to express an expansion, and so I can calculate this, and I know how to deal with this action only in a perturbative way. But now, if I do the perturbative expansion, I find that most of the quantities which are there are infinite. And this prompted, for example, Dirac to abandon the idea of doing quantum field theory. Feynman and Schwinger insisted in doing it, and you have to deal with these infinities. Dealing with these infinities means that you have to subtract them. And so you have the mathematically horrible but very interesting way of dealing with this field theory, in which you subtract infinities to get a finite part. And this finite part is what you actually measure. So if you write the action before renormalization, all of these numbers are really infinity. It's only when you subtract things that they become finite. Now, subtracting two infinities is obviously a procedure that you have to do correctly, because subtracting two infinities you can get anything. So you have to understand what this happens. And what happens really is that these quantities, which we call coupling constants, are not really constants. And so they are called running coupling constants. So they are quantities which depend on the energy at which you are doing your experiment. And there are some precise ways in which these coupling constants run. Precise also, they are perturbative. You calculate them with these Feynman diagrams. And so at some experiment, you will find some certain coupling. If you do the experiment with a different energy, this number will be slightly different, not tremendously different. But of course, if you go from low energy to the energy of LHC, size starts being sensible. And if you extrapolate to the Planck mass, now the problem that was that Kohn at that period in early 90s was not appreciating these issues of renormalization. And he found relations between various masses, which I will now describe something. And they were classical relations. So say that if a mass of a particle is twice the mass of another particle, you say, oh, okay, the mass is twice. Well, no, because in the running, at different energy, this factor of 2 will not be there, unless there is a symmetry, unless there is a reason, a more profound reason for which this is true. So he didn't appreciate this really, and he went to CERN. Since he was a field medal, he was given a big talk. And he said, okay, I predicted the mass of the Higgs. It was not the same prediction that we have now. And then people said, well, you are predicting the mass of the Higgs at which energy? So you write an action with some relations, and then you have to tell me at which energy you are doing this. And he really didn't know. Now he knows. The funny thing is that I thought that thing is that now I'll show you a little bit the renormalization issues. There was a paper that he wrote with Chamseddine Cohn and Marconi, where he was doing all the calculations, which as I will do them now with all the renormalization, and I was convinced that actually Ali Chamseddine was the one that was doing the physics. And but I met Alain at some conference, and there was something which we did the same thing. We repeated everything in. See, I may sound that everything is unwavering, but after all, I sit down. So we were repeating with my student Agostino Devastato all of the calculation, all of the running of the solution of this. They are ordinary differential equations. So the running, and there was something that we were finding something different. What happened is that in the paper they were not describing something very well. So I asked Alain, and he opened the mathematical file which you saw also, which clearly he had written, and uncharacteristically for a mathematician, the file was pristine. My files on mathematics are all messy, and everything, he had titles with sections, subsections. I don't know if you use Mathematica. I basically write something, and then from time to time I put a comment there. No, he was in section, and he had done all the calculations really as they should be done in the mathematics. The nitty-gritty, the physicist work, something that I am ashamed to say, I had my students basically doing, and he had done everything. So he had learned very well. Sorry, I moved. Yeah, he learned very, very well what to do. So now this issue of renormalization is certainly under control by Alain Cohn more than by me, that I taught this in some classes. So this is just an anecdote. Okay. The fluctuation of the Dirac operator introduced the bosonic fields, which are responsible, like the W, the Z, and they introduced the coupling to the fermions responsible for the breaking of the symmetry and give mass to the fermions. Now, this is the X mechanism. So we write, and I will be more specific in the future, we write down the Lagrangian reaction of the standard model with the term which break the symmetry, because this SU1 cross U1 is actually broken. The symmetry surviving is only U1, which is not it's SU1 cross U1, and there is a U1 which is generated by a mixing of the two the generators, and this is broken to the U1, to the abelian symmetry, which is electromagnetism, light, and the other bosons acquire mass with the X mechanism. This is a misnomer. Okay, now you know that X won the Nobel Prize with Engler and Braut, but these three people they did also some interesting, important contributions. It was at some point it was complicated who to give the Nobel Prize. Braut unfortunately died, but the paper was Engler and Braut, and so was given the Nobel to X and Engler. The Nobel cannot be given to the memory of people, so Braut didn't get it, but he was deserving it. It's written in the motivation, so it was deserving. Okay, now we should get number in a form which can be confronted with experiment. Now, quantum electrodynamics gets number out of renormalization, which agree with experiment up to 12 or more significant digits. So there is no doubt that quantum field theory with the subtraction of these horrible infinities work, because there are very few mathematicians that really do that. Probably Roberto Longo is one of them. He can deal with these things, not many people. The physics is very dirty, but works, because you get 12 digits is, of course.
Just one question. Ellen Kohns also had discovered some half algebra structure within the Feynman diagrams, right?
Yeah, that's quite a
Is
different
it
thing.
related to this kind of thing?
Not really. Probably. So I have that I don't see the connection. If you talk with Alain, he will probably answer, yeah, of course, because there's not me in these lectures. You are talking of this work with Dirk Reiner. Kreiner, isn't it? Okay. So we have set the stage. We have some ingredients. So we have an algebra, which is an almost commutative algebra. So which is C0, the functions on some ordinary manifold, times 3 by 3 matrices, quaternions and complex numbers. And this is the algebra. I have a representation of the algebra on this Hilbert space containing all the known functions. The representation is asymmetric, we can discuss. The details are in the exercise, but I don't want to do it now, and I don't think I will do because time is... and a generalized Dirac operator, which has information on the curved background of the continuous Riemann part, as well as the masses of the fermions. Really, they should say Yukawa couplings. Well, but there is a number for each fermion, okay? And, a number so that they have different masses, so otherwise all the fermions will get the same mass. I have chirality and charge conjugation, an action based on the spectrum of the operator in which we expand as a series. And now everything is cranking a machine because you have the algebra. With the algebra and the Dirac operator, where is the thing where I cancelled? You do the 1/4, and this is just commuting things. And then you write the spectral action. Then you go in the book of Seeley and of Gilkey, or in the manual of Vasilievich for the heat kernel expressions of the Seeley-DeWitt coefficients. You look at them, what they are. And so now the matter is only to crank a machine. Okay, so you crank a machine and you get an action. And this is the action. I am cheating a little bit. I could write it in more schematic form. But this is the action of the standard model with all the terms. It's taken from the paper of Kohn and Marcolli. It's very small so that you cannot see, but there are all the various fields here. You can see the W here. A is basically the photon. Then there will be somewhere appears the X and the Z particle, and somewhere are the gluons and something. So this is the action which describes how various particles interact with each other. They are all terms in the Lagrangian, basically of this kind, or of this kind. Okay, this is the mass term for a fermion. This is the interaction of a fermion with a boson. This is the interaction of the bosons with itself. So this is the kind of things, but not every boson interacts with every fermion, and the interaction between bosons is different if you are the W's and the Z, and then there is the X which gives mass to everything. But you do get the Lagrangian of the standard model, and the numbers which are there are all coming from the spectral action. Now, they say, okay, we knew the Lagrangian already. The Lagrangian of the standard model was known before. Now, however, all of the numbers which appear here that you don't see, the various constants appear are all fixed by the entries of df, which are the Yukawa couplings or masses, because the mass is really the Yukawa coupling, which is a number, times the x, which is a field. of the fermions and mixing. Okay, now the parameters of the X, which is a boson. So I am fixing all of the parameters of the fermions, but the parameters of the X are dependent on this, and they're not independent, as in the standard model. In the standard model, the bosonic part of the X field, so the X field interacting, has some constants, two constants there, which can be anything, and they have to be fixed by experiment. Here, no. They depend on the fermionic parameters. So you have a prediction on this number. But as I say, this number is, you have to say, at which energy you are making this prediction. And so we have a prediction on the X. Now let me say, this was a little bit what I said before. This Lagrangian is classical. One has to quantize and has to implement the renormalization. Okay, I will not quantize gravity, which is, this would give a non-renormalizable theory, and choose as a background the Minkowski, here something is missing, Minkowski space, just to make my calculations simple, and also because the experiments which are done at CERN are in a very weak gravitational field, so a very good approximation will live in Minkowski, unless, numerically, unless you are very close to a black hole, the curvature of space-time. For an experiment like smashing two particles, of course, for the Earth going around the Moon, the Earth going around the Sun, or the Moon going around the Earth, the curvature of space-time is important, but on the small thing, the gravity is a very weak force. So gravity in this room, compared with the electromagnetic, in fact, it's sufficient to do this, and you will pick up a piece of paper, because even a very tiny electrostatic charge is way superior. So the interaction, strong, weakened electromagnetic interaction compared with gravity in this room or at the CERN is basically not important. So renormalization means that all constant quantities in the action are a function of the energy, they are called running Coulomb constant. And the running is done by the beta function. This is a solution of an ordinary differential equation, which is calculated perturbably to first, occasionally second order in h bar by the endpoint amplitude, and this is the loop expansion. This is the Feynman diagrams that you may have seen. So if I want to know what's happening when I have the interaction of an electron, so if this is the physical process, an electron and a positron going into annihilating into light. This is the process, but in reality, the process would be an expansion, which this is the first term, then there are coefficients, and the second term here will be a loop expansion. So what is the first term? Here I have objects of this so this is an electron which arrives, emits a photon which interacts with the positron, and then they will go. And you see there is a loop here. So there will be a loop expansion, or there is another term which is this. So the photon makes emits, becomes a pair of electron and positron which re-annihilates, etc. Now this is really a graphical way of seeing, there are coefficients here, of seeing an expansion due to Feynman, so they're called Feynman graphs, and independently by Schwinger and Tomonaga. But Feynman did the graphical representation. And however, these coefficients become smaller and smaller the more loops there are. So one usually calculates, and they're difficult to calculate, because you have to calculate all of the possible things at one loop. So usually one calculates to first order, sometimes second order, you get to third order, and in some cases there are calculations up to sixth order, but they are simple processes. And of course, I didn't calculate, somebody calculates them. So from now on, I use traditional quantum field theory techniques. So I'm not using all the machinery. Something is being done now by Kohn and Sulecom on doing really the machinery applied to quantum field theory, but now I will not do it. So, first thing, one has to decide at which energy one writes the big Lagrange, and this will give a boundary condition. So if I write this Lagrangian, I write it at some energy, and then the running, which is a first order differential equation. So if I have one boundary condition, I can know the values at each. Now it turns out that the top quark mass is much higher with respect to the other particles. This is not 170, it's 150. So, versus 4 GeV for the bottom, which is the next highest. So the parameters and the flow are somehow dominated by the top quark, just because it's the heaviest one. Okay, so there are some corrections to this. Okay, now I get a boundary condition. And the boundary condition is due to the fact that when I cranked this machine, it wasn't evident in the thing, but I found that the coupling, the strength of the fundamental interactions, so the coupling constants of the strong, weak, and electromagnetic force, are equal. So the three forces are equal. They are not equal at low energy. We live at low energy. Actually, they are very different. The strong force is much stronger than the weak force. And then there is the other, I call it electromagnetism. The physicists will forgive me because it's really, it should be the either charge, but it's a U1, so electromagnetism is U1. So. Okay, now, experimentally is known that if there are no other particles appearing at higher energy, the three coupling constants are almost equal at one point, but they are not equal. And this is the plot. Now, this is an experimental plot. If I was really a phenomenologist, there would be some points here along this line which corresponds to various experiments. Now, it's a first order ordinary differential equation. So all you need is basically one point, but the theory works, so the various points at the beginning here, at this energy here, they are roughly along this line, and they are the three coupling constants. You will see that this is the coupling constants of the interaction. You will see that two of them is on a log plot. These labels are in the log. So this is 10 to the 16 GeV. We are around here with LHC. You see that two of those decrease. So the strong and weak force, which is stronger, the strong is stronger than the weak, but they are decreasing with energy. This is the strong force. You see that it's becoming weaker. This is calling asymptotic freedom. So at high energy, inside a proton, the quarks are actually free because they are at high energy. And one instead is increasing. And it actually, so this will go to zero at infinity, and this will go up towards something which is called the Landau force. However, we know that this is 17, 16, it is somewhere around here. That's why the plot stops. Something will happen. because at 10 to the 19 GeV, gravity is as strong as these interactions. Because you see, they were rather weak. Instead, gravity, which we don't know to quantize, so we don't have a plot for gravity, but we know that at 10 to the 19 GeV, the curvature of space-time is such that the effects cannot be ignored for quantum field theory. So somewhere here, and if you want, I have seminars about this. Somewhere here, probably there will be a phase transition. And the role of space-time will become important. So there will not be an almost commutative geometry. If we are right, there will be a fully non-commutative geometry, or there will be loop quantum gravity, string theory, or something we don't know yet. But this is what happens. Now, this construction says that there is one point in which these three numbers are all equal. And this is not true, okay? This is not true because there is this called the triangle, the unification triangle. It's not a point. However, the range is not that high. See, this is a full range, so it's around, this is a pure number, and so will be around this kind of number. So I can do the calculation, I can do the running of my action, assuming all of these values. It's an ordinary differential equation solved numerically what can also be solved analytically by a computer, so you can see what happens in all cases. So you can just take these objects and these quantities and do the running. So you write the action with this thing saying, so this is written at this range of energies with these values, and then tell me what are the values at low energy, and in particular, tell me what are the values which give the mass of the Higgs. Now, for physicists, the mass of the Higgs is not on the same footing as the mass of the other particles, so it's not a term, it's not really a mass, because the quadratic term in the action for the Higgs has actually the wrong sign. So the mass of the Higgs is, okay, I didn't write it. The mass of the Higgs is really a ratio between the interaction of the quartic term of the Higgs divided by the expectation values of the breaking, but this is under control. And so the Dirac operator contains all the data. It doesn't contain information on the Higgs mass. Actually, it's really the vacuum expectation value and the quartic coupling. One of those is fixed, was fixed by experiment long ago. The other one was not known. It was the one that was measured at the LHC. But we can calculate it from the fermionic mass parameters, Yukawa. They are dominated by the top quark mass. And so we have a prediction. This was a genuine prediction for the Higgs mass. And the prediction is 175 plus 5.8 minus 7.2. The uncertainty on this number is due to the fact that I have taken a range of values here, and there is an uncertainty on the experimental values which I put there, and there is an uncertainty due to the, no, that's all, those are the two uncertainties. They are asymmetric because some numbers can be bigger than the others. So you get a range which is between 170, 180, 168 or something like that. If, probably now this number could also be decreased because there are more precise measurements. Okay, and this number is wrong for a physicist. No one made a mistake in the calculations, and the experimental value is this one. This number is probably now slightly changed. This error is decreased because LHC is still taking data, so we have better statistics. So another sociological comment. I'm getting old, no? So I start doing all these things, telling you, but this is important. I didn't use mathematical rigor, and this may disconcert and also horrify mathematicians. And some mathematicians have this impression that twin physics can do anything. Who cares? But you see, we have stringent rigor, which is experimental verification. So we can do anything we want with a theory, and in the end we judge by a prediction. So if you do a crazy theory, and this is right, then you understand what it should have been. You clean it up. Otherwise you throw it away. There are lots of beautiful mathematical theories, perfectly consistent. Just nature has chosen not to do it, or probably there is a reason we don't know for which it doesn't work. Now it depends what you consider for what I'm doing. Now, if you take this as a purely mature theory, so I say, this is the theory, and then you take the result, then the result is wrong. That's it, let's go, we've done it. And this was somehow the point of view of, not so much of Alain Kohn, but the people in Marseille in the 90s and early 2000s. They said, oh, beautiful, we have everything, we have predictions, etc. Let's, there were papers which said theorem, the mass of the Higgs is. I never considered that. It's a nice idea, let's work on it. Now, if it's a tool to basically start a model, starting for first principle, this is remarkable, because I start with pure mathematical results. I get some input, and I get a number which is not 125, it's 170, but it's not, it could have been 3 times the mass of the electron. It could have been numerical factors. It's dominated by the mass of the top. So scales, natural scales there are 150. But you get numbers coming from ranks of matrices, and if you do the calculation, there are numbers which cancel each other, not enormous numbers. So, but instead of 150, you could have gotten 5 GeV, and that would have been killed immediately, or 5,000 GeV. Instead, you get the order of magnitude. But you start from pure mathematics. And so this is remarkable. And therefore, now we have 170, so now we know the mass of the Higgs. And this is a reason to understand in which direction one has to improve on the theory. And I immediately asked them to add that it is possible to reconcile things with experiments. But it's not a prediction, because we knew it already. And especially, we lose a little bit of predictive power, because we wiggle with the theory, and so we have to put another parameter. So now, what happens? Now, the prediction depends on the boundary conditions. And we are forced to use one in which the 3 coupling constants were equal at a scale. And this is true only approximately, but the picture which I showed is based on a running which starts from low energy and extrapolates to high energy. So as I say, here we have the data here, and we extrapolate this. Now, of course, the running of the coupling constant is an ordinary differential equation, so there are no mysteries there. But this is called the deep desert. What happens here? If I have another particle with a large mass, this will contribute to the interaction. It will introduce at one loop some terms here. Now at low energy, a very massive particle or a massive particle will not contribute. That's why we did fantastic things with quantum electrodynamics without putting the W particles in the game. Because we're at low energy, this particle is very heavy, so we can safely ignore. Okay, so if you have a big lorry, a car, and a motorcycle, and the motorcycle smashes into the car at some speed, it will probably move the car a little bit. But if there is the lorry behind, it will just smash against the lorry will stay put. If the motorcycle has a lot of energy, the car will get a kick very strong, and it may move eventually the lorry. It depends on energy. Also, baseball with sufficient energy will give enough energy to move a lorry. So you can consider the lorry. You say lorry, the truck. It's, American. If I say lorry in American, no one will understand. Yeah, a bit something. So you may consider the lorry to be an infinite mass, so like a brick wall, up to a certain energy. But then if you go to a sufficient energy, it's not a brick wall. And if there are particles very heavy, they start playing a role here. So this slope will not be this one anymore, but will change a little bit. So now this is called the deep desert, because at the moment the standard model doesn't predict anything. So it's called the deep desert because if that's it, if there is nothing else, then you don't get anything up to the Planck length, Planck's energy, where we know something will happen, but we don't know what. So it's like the desert, You know that there is something at the end of the desert, but there is nothing in between. This may be wrong. There will be oases. The desert is not a desert at all. There are lots of things going on. And if I change the field content, the running of all quantities will change. Okay, so if I put new particles, these three lines will change. Actually, they will change also in a semi-discontinuous way, because particles start playing a role at a certain energy, not before. And in fact, if there is supersymmetry, which doesn't appear to be, because at CERN they have not yet found it, not found it, or it's always not yet, because we don't know what's happening, then the three quantities will come together to one simple thing. Historically, many years ago when I was a student, the experiments were not that precise. So these three lines were thicker. So they were coming together, and this was considered a good thing for grand unification theory, because also grand unification, like SU5s, require a point there. So now this is, so if there is something else, you should get it. But now the something else is something that has to come out of non-commutative geometry. While normally you can put whatever you want. You say, X did that. Say, well, let's put a field of this kind and let's see what happens. We cannot put fields randomly because we have a structure. So we have the ingredients, as I say, are those. Okay, those are the ingredients. So I can add